Ladies and gentlemen, good evening all. Today we are going to look at organic chemistry. So what is organic chemistry? Organic chemistry is the study of carbon or study of organic compound and their properties. And in other way, we can also define organic chemistry as the study of carbon and its compounds. So it means that organic compounds are compounds of carbon. So you see, this is the real definition. So organic chemistry is the study of carbon and its compounds. So anywhere you see carbon and its compounds, so that compound is considered as organic compounds. So organic compound are compound of carbon, and remember when we said compound is a combination of two or more elements. Although generally we have some elements that they have carbon, but they are not considered as organic compound. Example of them we have like trioxocarbonate, cyanide compound, and metallic carbides. All those they contain carbon, but they are not considered as organic compound. So where do we get this organic compound? Where and where do we get them? Number one, we get them in fossil fuels. That is from the dead remains of plant and animals. You can also get them from plants directly, and we can also get them from animals. And then examples of organic compound, we have gasoline, oil, and sugars. And then what are hydrocarbon? Of course, organic compound or organic chemistry is classified into two. We have what you call hydrocarbon and non-hydrocarbon. So when we say hydrocarbons, it means that a compound that contain carbon and hydrogen only. So any compound that contain carbon and hydrogen only, so that compound is known as hydrocarbon. And we have non-hydrocarbons. So non-hydrocarbons is organic compounds that have other atoms apart from carbon and hydrogen. It means that in addition to carbon and hydrogen, other atoms are also present. Like for example, when we have ethanol, methanol, they have oxygen in addition to carbon and hydrogen. And when we have sulfur, thiols contain sulfur, and we have amide, they contain nitrogen in addition to carbon and hydrogen. So organic compounds are classified into two: hydrocarbon and non-hydrocarbon. Then therefore hydrocarbon are organic, but not all organic compounds are hydrocarbon. So you have to put this at the back of your mind. All hydrocarbons are compound, but not all organic compounds that are hydrocarbons. So meaning that apart from the hydrocarbons, there are also other class. That is why I said we have non-hydrocarbons. So non-hydrocarbons, they contain carbon and hydrogen and other elements. So now what is so special about carbon that make it very, very essential and unique in organic chemistry? So there are actually three reasons, and here we only have two. So one of the reasons is they have four covalency. That is, they can accommodate 4 electrons. They can share 4 electrons, so they undergoes strong covalent bonding. So because of that properties, they undergo strong covalent bonding. That is why carbon is essential, is very important in organic chemistry. And that is, in fact, there is no any other element in chemistry that although we have, but carbon is because of the lower atomic size, so their covalent bonding is very strong. So that is why they are so special in organic chemistry. And another reason why carbon is considered as special in organic chemistry is, number one, carbon have the ability to undergo catenation. What is catenation? When we say catenation, it means the ability of an element to form straight chain hydrocarbon, and they have the potential, apart from the forming straight chain hydrocarbon, they can also form ring chain. ring chain. They have ring, something like this. Let me just give demonstration. Catenation, that is, they have the potential to form straight chain, something like this straight chain. And also, apart from the straight chain hydrocarbon, they also have the potential to form branch chain, something like this. This is branch, so they can form straight chain and they can form branch chain, and at the same time they have the ability to form a ring chain, that is a cyclic compound. So that is catenation, something like this. You can have something like this. All this is the special properties of of carbon. They can form long chain, straight chain, and straight chain, branch chain, and ring chain hydrocarbon. You can have carbon a ring, something like this. You can have it something like this. This is a ring, cyclic, so they have that potential. So only carbon. And another reason why carbon is considered as a main element in organic chemistry, or it is so special in organic chemistry, is it has the potential to form single bond between carbon to have single bond, and also it has the potential to form between carbon to have a double bond. Only carbon has these special properties, and they have the potential to form triple bond. So this is so special actually. And remember, for whenever you have single bond, so single bond indicate one sigma bond, and if you have double bonds, one is sigma and one is pi bond, and if you have triple bond, so the middle one is sigma one and the one side by side are pi bond. Okay, so these are the three reasons why carbon is considered as a main element in organic chemistry. One, it forms special covalent bonding due to sharing of 4 electrons, and number two, it undergoes catenation, and number three, it has the potential to form single, double, or triple chain compounds. That is the three reasons why carbon is considered as a main element in organic chemistry. Okay, then we are moving to the next. So what are the properties of organic compound? What are the properties of organic compound? Yes, of course, organic compound, they have general properties. Number one, they are non-electrolyte. So when you say they are non-electrolyte, it means that organic compound do not conduct an electricity generally. And number two, they react very slow because of the covalent bonding. So if you ask the reason why organic compound undergo slow reactions, the reason is simple. Is because they have strong covalent bonding, so that's what makes them to undergo a very slow when they are reacting with other species of compound. Then they usually have low melting and boiling points, so they have low melting and boiling points. And number four, they are insoluble and immiscible in liquid, meaning that in water, meaning that if you take organic compound, like take examples of oil. If you have oil and you put it in water, what will happen? You will see that the oil is usually at the top while water is usually at the bottom, indicating that the water molecules is higher in density compared to the organic compound. They always demarcate. So because organic compounds are insoluble in water, but they are soluble in organic compound like ether, ester, chloroform, and the rest. Okay, and then that is this. Then which of the following are organic and which of the following are hydrocarbons? So we are going to have something like this. So types of chemical formula. So molecular formula shows the number of atoms of each element in a compound. That is the least informative formula. So we have, you know that we have what you call molecular formula and empirical formula. So molecular formula, it shows the exact it shows the number of atoms present in each compound. So it's not given the ratio. You see, like for example, propane. So what is the empirical formula? The molecular formula is C3H8. So it gives the exact number of atoms that are present in a compound. While remember, empirical formula is just give the ratio of the atoms that are present in a compound. So we have types of chemical formula. Look at this. We have different ways of representing chemical formula of a compound. So look at it. This is propane. So we we draw the structure. Look at it. We have 3 carbon and H hydrogen and 8 hydrogen. So now, for example, somebody might decide to ask you how many sigma bonds do we have here. You just count the number of atoms. We have 3 carbon and we have 8 hydrogen. So 3 plus 8 we have 11. So 11 minus 1 we have 10. So 10 it indicates the number of the sigma bond. So if you want to get the total number of the sigma bond in a compound, what you do is you take the number of atoms of that particular compound, you add everything and you subtract it by 1. That will exactly give you the number of the sigma bond. So structural formula, so we also have structural formula apart from the molecular formula. So structural formula shows the number of atoms of each element and the arrangement of the atoms, and it is most informative compared to, so look at it. This is actually the structural formula. This is the structural formula of propane. The structural formula of propane, that is this. Why do we say that it is the structural formula of methane? It's simple, because if you now look at this one, you will realize that we have okay, so why do we say that this is the structural formula? Is simple, is because okay, why do we say that this is the structural formula? Is simple. This is because if we now look at this very well, we'll now see that we have just the arrangement. We have the number of atoms and the number of atoms are arranged. So now that is this structural formula. It shows the number of atoms and the arrangement of the atoms. So it's most informative compared to molecular. It gives more information compared to molecular formula. Then we also have condensed formula. So generally this is a condensed formula. It didn't actually give the exact how the arrangement of the atoms are. So condensed formula is a combination of both structural and molecular formula. So each carbon is written with its constituent hydrogen atom. So look at it. First carbon with 3 hydrogen, third carbon, that is the middle carbon, with 2 hydrogen, and the last carbon with 3 hydrogen. So condensed formula is just trying to give an information on both the structural and the molecular formula. So each hydrogen atom is attached to its main carbon. So look at it, this is the structural formula, and this is the condensed. This is the structural formula. This is the structural formula, and this is the condensed form maths. Okay, then homologous series. What is homologous series? Homologous series is the series of the reaction in which each individual member of the group is differ by the next member by CH2. So like for example, look at this homologous series. If you now this is let me you see, these are the members of hydrocarbons. You see table Q shows the general formulas and the structures for 3 families of hydrocarbons. Of course, hydrocarbons, they are also classified into 2: saturated hydrocarbon and unsaturated hydrocarbon. When we say saturated hydrocarbons, it means hydrocarbons that have single bond between carbon to carbon atoms throughout the compound, while unsaturated hydrocarbons, they are the one that have the deficiency of hydrogen atoms. And this deficiency of hydrogen atoms, in the case of alkenes, they have deficiency of 2 hydrogens, while in the case of alkynes, they have deficiency of 4 hydrogen atoms. So, and these are their general formula. So look at it, alkenes, between carbon to carbon you have single bond, and their general formula is C2H2N plus 2, while alkenes have a general formula of C2H2N, and they are double and between carbon to carbon is double bond, while for the alkynes they have carbon to carbon triple bond. So this is how the way we can actually try to give an information about the members of the hydrocarbons, the three families, which is alkanes, alkenes, and alkynes. And in the homologous series is just trying to give us an idea. The series is usually occur between each and every family. Like for example, if we take ethane and propane, you'll see that the differences between ethane, propane is just the differences of two carbon atom. Sorry, it's just the differences of CH2. We'll see that. So this is alkenes. Alkenes generally have single bonds between carbon to carbon, and these bonds are considered saturated. So it's considered saturated because they have the maximum number of hydrogen atoms attached. Each carbon needs 4 hydrogen atoms. And remember that each bond represents one pair of shared electrons. That is 2 electrons total per bond. Yeah. So now this is a general formula CnH2n plus 2. Example, we have methane. So, and alkenes, they have double bond between carbon to carbon, and their bond are considered unsaturated, and their general formula is CnH2n. So remember, the first one that is for the methane is alkane is CnH2n plus 2. So we have butene as an example of that group. Then alkynes have triple bonding between carbon to carbon, and they are also considered unsaturated. Their formula is CnH2n minus 2. Example, we have propane. Then the next thing is, how can we name hydrocarbons? That is the IFAC name. To name simple hydrocarbons, straight chain only, carbon to hydrogen, we will put information from table P and Q together. So these are the information. So ladies and gentlemen, what I want you to understand, we have what we call alkyl group. Alkyl group generally have their own formula, and therefore their formula is CnH2n plus 1. And for you to get alkyl, you just have to remove 1 hydrogen atoms from alkane. So alkanes family, we have like methane, propane, methane, ethane, propane, butane, pentane. So if you remove 1 hydrogen from methane, you will have methyl. If you remove 1 hydrogen from ethane, you have ethyl. If you remove 1 hydrogen from decane, we have decyl. So look at this. Table P shows the prefix to determine how many carbons are in a compound. So now what I want us to understand is we have a prefix. Meth means a compound that contains 1 carbon. Eth means the one that contains 2. Prop means the 3. Pent means 5. So this is just trying to give us how the prefix are in trying to actually name the member of course, all organic compound. These 10 prefix are very, very important, and you name organic compound based on this, but depending on the functional group. If it is alkene with 2 carbon, you name it ethane, it will end with ane. And if it is alkyne, the one with triple bond, and you remove, let's say, from let's say alkyne, from alkyne, if you remove, let's say, if we look at the cane, so the cane in alkyne, it will end up with that yne, so it will be decyne. Okay, then steps in naming unbranched hydrocarbon. What are the steps? 1. How many carbon atoms are in the longest continuous chain. So if you have the compound, the first thing you need to do is actually try to know the number of the carbon in the straight continuous chain is very essential, and find the prefix for this prom. Like for example, we have 1 1, so we have 2 carbon, so the longest carbon here is 18 because there is no double bond. If there is double bond, it will be ethine, and if there is triple bond, it will be ethine. So you see, if it is an alkane, simply add the suffix ane to name. So this one are 2 carbon, so it will be alkane. So ethene, sorry, not alkane, ethane, because the carbon to carbon is single bond, so it means that you have ethane here. Then okay, so if it is an alkane, so you add ane, so this is ethane. Okay, the next thing is the step 3. How can we name hydrocarbons? That is the IFAC. If it is an alkene, you must first indicate the location of the double bond if you want to name alkene. And if the molecule has more than 1 carbon, do this by numbering the carbon on the chain and starting the lowest carbon where the double bond is located. Then add the suffix ene to the name. So now look at this compound. If we are going to name this, we have 2 ways. Sorry, we have actually we have to count the number of the carbon chain. So you see, this is, if we start from here, we have 1, and we have 2 here, then we have 3, we have 4, and we have 5. So you see that we have 5 carbon atoms. So from here, if we count, this is 1, this is 2, this is 3, 4, 5. So advisably, if you are going to name this, so you see 1 2, it means that if you follow this direction, 1 2 3, 1 2, so the carbon here will be one, it will be the one bearing the double bond. So this is 1 2. So it means that in carbon 2 we have double bond, and the longest chain we have, the number of the carbon is 5. So since it is 5, it is going to be pentene because of the double bond. But we must indicate the position of the double bond. So we have 2 ways in writing this. We can decide to say pent 2 n. You can decide to say pen 2 n. If we said pen 2 n, this, and we have to add dash. So this 2 means that at carbon 2 we have double bond. And in the other way, we can say 2 pentene, meaning that at carbon 2 we have double bond. So we can do this. And so also we can name it in also another direction. If you start counting the number of carbon from this direction, 1 2 3 4 5, so you see that the carbon here at number 3, if you follow it in this direction, we will see that it is carbon 3 that is bearing the double bond. So it means that it will be pen 3 in, or 2 pen 3. So but remember, we have to take the one with the lowest number. So 2 and 3, which one is the lowest? Is 2. So this one is correct, the other one is wrong. Okay, so, and if it is an alkyne, you must first indicate the location of the triple bond. So remember, for even the other one, the position of the double bond must be indicated. And if the molecule has more than 1 carbon, then do this by numbering the carbons on the chain and starting the lowest carbon where the triple bond is located. Then add the suffix YNE. Okay, so now look at this one. If we start numbering from this direction, look at it from this, it means that it is at carbon 1 we have the triple bond. So it means that the name will be pent one ine, pent one ine, pent one ine, or you can say one pentine, yeah, you can name it like that. Okay, then that is for this. And if you start numbering from this direction, you see the 1 2 3 4 5, so it at carbon 4, so pent 4 1 for pent 4 9. I think it's wrong. We have to take the one with the lowest carbon, with the lowest number. Okay, then molecular formula name. Okay, this is just okay, so now the next thing that we are going to look at is isomers. What is isomers? Isomers are compounds that have the same molecular formula but different structure. Look at it. And isomers have the same molecular formula but are rearranged in a different structure with different chemical and physical properties. So at least 4 carbon must be present in a molecule to have isomers. So you cannot have isomers in compound with less than 4 carbon atoms. So we have to know this. Methane, ethane, and propane do not have any isomer. So butane is the first molecule to have isomers. The larger the molecule, the more isomers the molecule will have. Yeah. So 3 ways to make an isomer. So these are the 3 ways to make an isomer. Number 1, make a branch. If you have a straight chain, you can decide to make a branch. We'll look at that in the practical. Then you can also move a branch from one point to another in the compound. And you can also move a multiple bond. That is a double bond or triple bond. If it is at carbon 2, you can change it to carbon 5. So what I want us to understand here is the more the number of carbon atoms in a compound, the more the number of the isomers. So you see this is pentane, but methyl group hangs off at carbon 2. So we now take methyl group from the pentane and change its position. We attach it, we make branch at carbon 2. So it will now change to 2-methyl butane. Then so also at the same time from that the same pentane, we also remove 2 different carbon atoms and take it to that carbon 2 at the same time. So you see it now changed to 2,2-dimethyl propane, because at methyl we have at carbon 2 we have 2 different methyl, so that is why it is 2,2. So there are 2, that is why we attach di. So I have 2-methyl, 2,2-dimethyl propane. Yes, that is pentane isomers. We have at least 2. Okay, yes, 2. So look at another one. This is also a different isomers of pent1-ene. Pent1-ene. Look at it. The other one is now changed. And the next thing now that I want us to understand is, you see, we now change the position of double bond to carbon 2 in the second one. That is, look at it. It is here, and it now changed to this to remove the double bond. And here, after the double bond still remain where it is, but methyl group, a branch is now attached. Then also look at it. The branch CH3 here is changed to another carbon, and then this one also. So these are the pentene isomers. So how can we name and draw substituent hydrocarbon? So we are going to stop from here.